Welcome to our business track of the Data Science Salon YouTube channel. In this talk, we have Mirik Iqbal, Senior Data Scientist at Etsy. Two tower approaches have become prevalent in the industry for both search and recommendations over the last few years. These methods employ metric learning to enforce a structure on the embedding space, which captures a specific type of similarity. Fast retrieval via approximate nearest neighbor lookups is then available in real time. Mariam will review the loss functions and sampling strategies employed in the industry to enable these methods, how they are deployed, and why they are so powerful for information retrieval. Enjoy the presentation.
Hi, my name is Miriam. I work at Etsy as a senior data scientist on the recommendations team, and I'm going to be talking today about metric learning and how it's being used in recommendations. So let's first do a quick review of what recommendations are. Recommendations are used widely in e-commerce and also on media streaming platforms and in various other places. We differ a little bit from search in that we have low intent. What does that mean? In search, the user is submitting a query that is expressly telling the system what it is that the user is searching for. For recommendations, we're making the assumption that somewhere in the user's history is some indication of what the user is going to be interested in. So it's very low intent. There can be a confusion there if the user just bought a one-off gift for another friend, or if the user has done a purchase in a category that they aren't going to be purchasing in again. So it's considered very low intent. There's also a lot of different placement options for recommendations. So at Etsy, we place them on our home page. We place them on our product pages. We also place them on thank you pages once you've made a purchase, and they're even used for marketing. There are also various different objectives for different recommendations. Sometimes you're trying to surface to a user an item that they are likely to co-purchase with a different item. And the objective there is try to get the user to buy more than one thing. Sometimes we're trying to prevent the user from kind of giving up. So if they've performed a search and they've arrived at a product, but they're no longer interested in that product, rather than allowing the user to go back and make another search, we want to make it a little easier for them. So we want to surface some substitutions for that product. There are also different archetypes of recommender systems on how to build them. So let's talk a little bit about that. We've got collaborative filtering. Here, the idea is that we want to group together similar users, and within those groups, we can then kind of recommend one another's purchases to them. So here, let's say we've got a blue user and an orange user. They're both interacting with the same sock, so we can assume that there's similarity between these two users. Then we can recommend the blue user's mug to the orange user. So here we're not even interested in what the items are themselves. We're just trying to group together the users based off of behavioral data. So are they kind of interacting with the same kinds of things on your platform? Then there's content-based approaches, which are mostly interested in trying to understand the items themselves. So if you're looking at a cork hanging planter, we're probably going to want to recommend things that are within gardening rather than things that are within clothing. So something that's more similar to the items that I'm already interacting with. Then there's the hybrid set of approaches, which kind of combines both behavioral and content data together to produce recommendations. So let's dig a little bit deeper on the collaborative filtering specifically. So when we have collaborative filtering, there's a couple paradigms within that itself on how to approach the problem. The first one would be we create a really large sparse matrix. So our large sparse matrix, the rows of it are the users and the columns are the items in your catalog. Anytime that a user purchases an item in your catalog, in that matrix, you put a 1. Everywhere else gets a 0. The assumption with matrix factorization methods that function over this large matrix is that there are zeros that should be ones. And if we can figure out which ones those are, we can present that item to that user. So it's kind of like a matrix completion. The other family of approaches actually assumes that the user's behavior is a sequence similar to a language, and we want to predict like the next word in that language, in that sentence of the user. And so we're kind of grouping together users who have similar sequences of behavior. Then content-based filtering actually functions mostly on the data about the items themselves. So this is popular in search, where we're trying to do like text-based retrieval. Here we would assume that some item that you have purchased has similar title or similar attributes or similar reviews to something else in the catalog, and we can present those items to you. We can also do this based entirely on image or a combination of image and text, such that we're presenting to you other items that have display images that are similar to the ones that you have already looked at on your platform. Another set of approaches takes into account taxonomy. So there might be taxonomies that lend themselves naturally to repurchase. So that could be something in like a perishable like food. So maybe you want a repurchase around tea. So we might recommend something that you've already purchased to you. And then there's also complementary based recommendations. So somebody might purchase a coffee table shortly after purchasing a couch. That might be a common pattern. And so we might recommend things that are in related taxonomies. Each of these different approaches has its own drawbacks. So the collaborative filtering based approaches have low coverage, but they have high accuracy. And what does that mean? So for the collaborative filtering based approaches, we can only really model items that have already been purchased on the platform. And so anything that's new to the platform or doesn't have a strong user history isn't going to be modeled by these approaches. They are high accuracy though, in that the user's previous history is usually a good indicator of what the user's next history is going to be. So they usually do pretty well. The content-based approaches, on the other hand, have very high coverage but low accuracy. They have high coverage because we are usually using features into these models that are present for all of the items. So all of the items on your platform are usually going to have some kind of a title, or they're going to have some kind of an image. And so if you're building a model that is relying on the images or titles of your items, it's going to have pretty complete coverage. These and recommendations are not usually the highest accuracy ones. The reason being is because we are working in that low intent space where we aren't given an explicit definition of what the user is looking for, and our content data is usually flawed. And so usually the attributes or the images aren't perfect representations of the actual item being sold. And as such, those are lower accuracy models. The reason we want to look at hybrid approaches is because they can combine all of the data used for the content-based and collaborative-based methods together into one model. So we can make use of the behavioral, the text, the image, and categorical data. And categorical data can be not just on the item side like taxonomy, but also on the user side, such as demographic information. There are non-neural network-based approaches that are hybrid, like factorization machines, but I'm not going to discuss those. I'm going to focus mostly on the neural net ones. So there are several different types of neural network-based approaches within the hybrid paradigm. The first one we'll discuss is the conditional variational autoencoder. So conditional variational autoencoders actually build on the matrix factorization methods, and they condition their objective on some content about the items themselves. The wide and deep methods are trying to simultaneously memorize the user's actions based off of the IDs of things they have interacted with, similar to a collaborative filtering method, but then also build a deep representation of the content that describes those items. The last approach is the metric learning paradigm, and those are the ones that I'm interested in discussing today. In metric learning, what we're actually doing is trying to create representations of all of the items And then in those representations, we want to build an embedding space such that things that are similar are closer together and things that are dissimilar are further apart. So the idea of metric learning is that we're going to learn an embedding space where in that embedding space, we are actually capturing the similarity of the items in our catalog within the distances themselves. So let's talk a little bit more about metric learning and the complications of applying it to recommendations. So I said that for metric learning, what we're going to do is build an embedding space where similarity is captured in the structure of the space itself. But what does it mean to be similar? So if we're looking at these 4 listings here themselves, the rows have a similarity in that they're the same taxonomy. The columns have a similarity in that they're things that could be purchased together and worn together, so they have similar style. And then the diagonals also have a similarity in that their color schemes are similar. So which of those would I want to drive apart and which of those would I want to drive closer together? It's a little ambiguous. There's a further complication here where we're not actually receiving positive and negative labels from the user. We're just looking at the user's behavior and we're assuming that some of their behaviors are positive and some of their behaviors are negative. So as an example, say I go on Etsy, I search for a linen dress, I see one that I really like, I purchase it. As the training data, I now have a single purchased listing here and a surrounding set of listings that weren't purchased. Are all of the surrounding the non-purchased listings negative then? Because some of them might actually still be relevant to the user. For example, one of them is actually the same item but at a different size, or some of them the user might not have even looked at because they didn't scroll far enough to see. So how we infer the user actions is really important on how we're going to end up labeling the data itself, since we don't have explicit labels. So how can we even enforce similarity in such a space? We can try to approach it in a few different ways. What we can do is try to sample the training data itself so that it reflects the objective of the recommendation that we're trying to build. So if you remember, I was saying that the different recommendation systems actually have different objectives. Some of them you're trying to push a co-purchase, and some of the times you're trying to push a substitutable item in front of the user. So given that type of paradigm, whichever type of recommendation system we're trying to build, we'll try to pick a sampling strategy that allows for that. So we'll sample our training data and generate it such that it reflects the kinds of things that we're trying to build. And then we can pick the features for those specific data samples so that they're reflecting that they're a good representation of what we're trying to capture. And then, of course, we can pick the loss function so that it is help driving things that we think are similar closer together. So let's talk a little bit more about sampling strategies. I'm going to use an example from the paradigm of computer vision. Let's assume that I'm trying to build a classifier so that when it receives an image of an animal, it is going to label it as whether or not it is a gecko. And we're going to assume that we only are using pictures that are similar to the first 2 rows in this image. So we've got pictures of geckos, cats, and dogs. And we use this to train a model, and it does exceedingly well. Then we try to use it in the wild, and it gets this image of a chameleon, and it labels it as a gecko. This is called in computer vision the idea of a hard negative. And what that means is the chameleon is more similar to the gecko than the cat and the dog are, but it is still a negative. So it's something that the model should be embedding close together, but is still a negative. Those are considered hard negatives. What would that mean in terms of recommendations? That could mean that there are 2 items that are both skirts that are both corduroy, but one of them is relevant to the user because the user purchased it, and one of them is less relevant to the user. So those items should be close together, but one should be closer to the user, such that you can then delineate what is the positive and what is the negative. There's a further complication in terms of sampling when we talk about sampling for recommendations specifically, in that because we are taking our data from what the users have already done and trying to build a recommendation system off of that, then we might end up in a situation where we are biasing towards what is already being displayed by the current model. So what that means is maybe I'll take 3 months of purchase data off of my users to try to build a recommendation module that recommends things that the user is going to want to purchase next. I now have a set of data where all of the positives and negatives are taken as output results for the current production model. So how do I get around the fact that the items that have never been interacted with on my platform or never been recommended by my platform can't be represented or aren't represented in my training data? One way to get around it is to do a random negative sample. And what that means is take a sample of negatives or class label 0 just randomly from your entire catalog. This can help in that you are now getting a representation from those listings, but what's happening is they're actually getting penalized because they're negatives only, not positives. You can counteract that by then taking a set of negatives from within your batch itself. So the positives in your batch can serve as negatives for one another. And that can help counteract any penalization that might be happening from your random negatives. And so you're going to have to find a kind of happy medium between those two sampling strategies. So once we pick a sampling strategy to produce all of our samples for our training data, we can then pick a architecture. So the architecture that we'll be using that is commonly used in metric learning for recommendations is a 2-tower architecture. This is similar to, you might have heard of twin architectures, but here we don't actually share the weights across the 2 towers. The weights are kept separate. So each tower is considered an individual deep neural network that is functioning over either the users or the items in your catalog. The items in your catalog are then indexed and are kind of the things that you're doing a search against. And the users are considered like a context that you're using to search in that index. And to get the benefits of a hybrid system, we want to pick features that are both from the behavioral data and the content data. So as an example, we might pick for both the users and the listings some representation of IDs. Like the users can be represented as all of the IDs that they have ever clicked on. The listings can be all of the IDs for the users have clicked on them. And then you can do a combination of attributes or item titles or taxonomies for both towers to get an idea of the content that the user is interested in and the content that that is indicative of the item that we're trying to embed. Once we have the architecture and the samples, we need to pick a loss function. I will say there is a paper from, I think, 2016 that highlights that even a simple loss function with a very good sampling strategy performs equally well to a complex loss function. That being said, I'd like to talk about 2 specific types of loss functions that are used. Here we've got the softmax loss functions, which are kind of like a multi-class classification. So it approaches it assuming that each item in your catalog is a class and there is one correct class to label it for each user. This is similar to trying to do an argmax or trying to maximize the probability of a specific item getting selected by the user. And you can kind of think of this in terms of the recommendations paradigm as being like a pointwise model. The other type of losses are contrastive losses, and there are several here. You can use the hinge loss or the triplet loss. The idea here is that we are trying to compare positives and negatives and maximize distances in that learned space. So we want to maximize the distance between a negative and an anchor and minimize the distance between a positive and an anchor. So it's more similar in terms of the recommendations paradigm to a pairwise loss function. And then there are other loss functions that actually function over whole sets of listings rather than pairwise or pointwise, which would be, I guess, not necessarily listwise because it's not actually trying to order them, but is trying to function on a cluster. And so what these do is actually pull apart class labels within the learned embedding space. How this could be useful in recommendations, you could imagine that you're trying to pull whole taxonomies of listings apart in your embedding space so that each cluster within your learned embedding space is a distinct taxonomy. So two methods for doing this would be the soft neighbors loss or the magnet loss. So given the type of recommendation that you're trying to build, you're going to pick a combination of your loss and your sampling strategy that helps you achieve the objective that you are trying to produce, whether that be a co-purchase objective or a substitution objective, and is best at handling the biases that exist within your data set. So let's talk a little bit about how you would evaluate the model that you have trained and productionize it. Standard evaluation metrics that are used in recommendations and search are recall. Recall is of the things that the user has purchased, how many of those did we actually recommend to the user? For the AUC, which is the area under the curve, it's under the receiver operating curve or characteristic. And what's being measured there is if I take a item that the user purchased and I take an item the user didn't purchase and I put them through the model, what's the probability that the model will score the purchased item higher than the non-purchased one? So this can be really good at comparing models against one another. And then there's also the NDCG, which is short for Normalized Discounted Cumulative Gain. Here we assume that each true positive has a gain associated with it, and we're going to accumulate them across many users. We're going to discount them such that each position of recommendation has decreasing value. So the first position that's shown to the user has the highest value, and so on and so forth. And then depending on where we put the true positives, you get a product of the gain associated to that item and the gain associated to that position. And then we normalize these scores across the users by taking the maximum possible score that a recommendation algorithm could have gotten for that user and divide by that. That helps us kind of compare situations in which the user has lots of purchase history into situations where the user has very few purchase histories. So this kind of normalization helps in that situation. All of those evaluation metrics are usually done on the user's history, though. And so what that means is if I take 3 months of training data, I will be maybe reserving the last 2 or 3 days as my evaluation. But that means that it actually is previous history shown to the user. And what that means is if there's a new model that is able to surface something that is actually more relevant to the user, but the user never actually saw before, that these metrics will actually score that model as performing worse because they are dependent on what the user has already seen. So for that reason, you also want to evaluate what the model itself is learning and evaluate the embedding space itself. To do that, you can kind of evaluate the distances of positive and negative samples that you set aside in advance. So maybe you have a set of samples of things that you know should be close together and a set of samples that you know should be further apart. And you measure their distance per epoch and see if they're being driven together or further apart. And then you can also measure their distance in the learned embedding space to see what is happening to them. And then you should also look at the results based off of your clustering. So if you're trying to produce substitutable items and you perform your KNN on your learned embedding space and you see that the items that are being returned are from very different categories. So say I have a hat and I do a KNN lookup within the embedding space and I returned shoes and a t-shirt, that's probably not a good substitution for that hat. But if I'm trying to do a co-purchase based model, then that might actually work out better. I might be capturing the style of those items together, and they might actually be more likely to be co-purchased. So taking a look at the data that's returned from your nearest neighbors is good. And the way you avoid doing that manually is to make use of your structured data. So get an idea of, do you want your taxonomies to be mixed together? Do you want them to be separated? Are there attributes you want to make sure are conserved in your neighborhoods that are learned? So once you have evaluated your model and you want to productionize a version of it, how do we go about doing that? What we actually end up building is a part in batch and part in real time. The part that's performed in batch is usually over the items. So we will in batch, maybe you're doing a nightly training. Every night you will do a inference over your entire catalog of items and produce the embeddings. You'll take the embeddings and you'll produce a nearest neighbors lookup index. We don't do a full nearest neighbors because we have millions and millions of products, so you'll probably end up doing an approximate nearest neighbors. Of that, there could be like a hashing-based method or hierarchical navigable small worlds method. Each of those are ways to do the approximate nearest neighbors. Once you have the approximate nearest neighbors index, you can host that live, and in real time, you can take the user embedding and use that as a lookup within the nearest neighbors index, and that'll produce for you the recommendations that you want to show to that specific user. Thank you so much for letting me talk, and here are references to the papers that I used. The two-tower approach and the metric learning approach is very prevalent, so there are lots of different papers here.
That was a presentation by Miriam Lacroix, Senior Data Scientist at Etsy. Miriam reviewed the loss functions and sampling strategies employed in the industry to enable the two-tower approaches, how they are developed and why they're so powerful to information retrieval. If you enjoyed this presentation, make sure to subscribe to our channel below. Thanks!